Today's electronic designs almost always include serial bus control. In almost all electronic industries, including consumer, automotive, aerospace and defense, and medical, embedded serial buses, including I2C, SPI, and UART, are utilized in designs to control and monitor subsystems.
And then there are additional serial buses found in the automotive and industrial automation industries, including the CAN and LIN buses that are used for longer distance serial communication with higher levels of fault tolerance due to the additional safety requirements in these industries. Using oscilloscopes that can decode and trigger on these embedded and automotive serial buses is imperative for most engineers working in these industries today.
Hi, I'm Michelle Tate, Product Marketing Manager for Keysight Oscilloscopes. I'll begin by showing a few quick demonstrations of the HD3 oscilloscope decoding and triggering on common embedded serial buses, including I2C, SPI, and UART.
And I'm Johnny Hancock. I'll follow up Michelle's demonstrations with some demos of the HD3 scope capturing, decoding, and triggering on common automotive serial buses.
Here's an example of the HD3 decoding and triggering on an I2C serial bus. This is the clock signal, and this is the data signal. Below the waveforms, we can see the time-correlated decode trace. And at the bottom of the scope's display is the protocol lister table. The HD3's 7-in-1 instrument integration displays this in a similar manner to a standalone protocol analyzer. Let's look at another serial bus. This is an example of decoding and triggering on the SPI bus, sometimes called SPI. Since SPI buses have 4 digital input signals, I use this scope's digital channels to capture these signals. Scopes with both analog inputs based on high-resolution ADCs plus digital inputs with 1-bit resolution are called mixed signal oscilloscopes, or MSOs. All HD3 oscilloscopes come with the MSO capability as standard, so if you already use one of Keysight's 16 digital channel MSO cables, you get this capability for free. And finally, here's an example of decoding and triggering on UART, which stands for Universal Asynchronous Receiver Transmitter. With this serial bus, there are data lines called transmit and receive, but there isn't an explicit clock line. The clock is essentially embedded within each of the data signals based on a fixed and known baud rate. UART can be decoded in either hexadecimal format, as you see here, binary format, or ASCII. Over to you, Johnny, to demonstrate decoding of automotive serial buses with the HD3 scope.
As I mentioned earlier, there are 2 big differences between serial buses used in consumer electronics as opposed to those used in many automotive applications. One is the physical difference that serial buses must transmit and receive signals reliably. The other big difference is safety requirements. Common buses used in the automotive industry that meet these more stringent error recovery and transmission requirements include the LIN bus and CAN bus. The CAN bus has various generational variants, including Classic CAN, which has been around for almost 40 years and is still very much entrenched, CAN FD, which was first introduced about 10 years ago, and more recently, CAN XL. This is an example of the HD3 oscilloscope decoding and triggering on a classic CAN bus. So here you can see where arbitration is occurring, where the signal goes down to a lower dominant level at the beginning of the frame when the frame ID is being transmitted, and down here at the end of this particular frame, it's frame ID 211, is the acknowledge bit. Now in the decode trace, of course you see the frame ID, which we are triggering on this particular frame ID 211. DLC equal 8, data link code 8, says there are going to be 8 data bytes following the DLC. And here you see the 8 data bytes followed by the CRC, currently color-coded in blue. That means it's correct. Now if it was red, had red font, that would indicate a CRC error. Now if I scrunch more frames on screen by changing the time base, we can see more frames down in the protocol lister. So now it's decoding symbolically with the DBC file. The frame we were triggering on, 211, we're still triggering on that frame, but it has a name of brake torque, and we could set the scope up to trigger on message names as well. We could zoom in and further and see the various signals within this frame, along with signal names, transfer functions, and units. Now, you may have noticed occasionally we see some red error codes popping up. There's one. Sometimes you see them in the protocol lister. One of the error codes I know that's there is a stuff bit error. Let's now set the scope up to trigger on a stuff bit error. So I'll go into the trigger menu, change from triggering on a frame ID, and down here you can see the various error conditions we can trigger on, including error frame, acknowledge error, form bit, stuff bit, and CRC field error. The scope can also be set up to trigger on specific bus errors. Let's select a stuff bit error, and there it has triggered on a stuff bit error. If I zoom in and take a close look, this is a stuff bit error. It was at a recessive high level for 6-bit periods. The maximum allowed in CAN is 5-bit periods. The HD3 oscilloscope also supports triggering on and decoding the newer CAN FD bus, as you see here. FD stands for flexible data, which means that more data bytes can be transmitted during each frame, up to 64 bytes, and at a faster bit rate, up to 8 megabits per second versus just 1 megabit per second with classic CAN. Here you can see the arbitration field, which in this case is being transmitted at 500 kilobits per second, followed by the data phase, in this case 64 bytes transmitted at 8 megabits per second. So you can pack more data into a single frame running at a faster rate to reduce overall bus load. The most recent variant of the CAN bus is called CAN XL, which stands for extended length. The HD3 also supports this more recent and more robust version of the CAN bus. As you just saw in these demos by Michelle and myself, the HD3 supports triggering and decoding on a broad range of serial buses for a variety of applications to speed your debugging. Thanks for watching this demonstration of the HD3 oscilloscope. Although this demo focused on some of the benefits of using this scope for embedded designs in consumer electronics and automotive applications, this scope can be used for a broad range of industry applications where high resolution, low noise, and support for common serial buses are important. The HD3 oscilloscope comes in bandwidth models ranging from 200 megahertz up to 1 gigahertz. This scope samples at a maximum rate of 3.2 gigasamples per second across all channels simultaneously, along with 100 megapoints of acquisition memory for each of the 4 channels. Perhaps the most important attribute of this oscilloscope is its 14-bit analog to digital conversion, along with a low noise floor at under 50 microvolts RMS at the full 1 gigahertz bandwidth. This oscilloscope also supports a wide range of advanced analysis features, including zone trigger, pass-fail mask testing, and serial bus decode and triggering as demonstrated in this video. For more information about the HD3 oscilloscope, visit the URL listed on your screen. Thank you.